Thank you for the introduction. Okay, hello everyone. Thanks for joining. Today we will be walking you through the journey of Blinkit and how it uses Trino Iceberg Connector to enable our analysts to build and maintain their own data marts at scale. Hello, my name is Shubham, along with my friend Bhanu. We work as data platform engineers at Blinkit, making systems reliable and scalable. Okay, so to set the expectations for the talk, we will be touching upon the following key points during the talk. Firstly, the scale and structure of data at Blinkit, and what was the role of data marts and why are they essential in our ecosystem? And then we will be saying ki why did we go ahead with Trino Iceberg connector only? And what were the implementation details and the challenges we faced during that? And lastly, the impact it had on our organization. Over to Bhanu.
So before we start talking about the Iceberg connector and how we used it, let me just briefly touch upon the companies. So Zomato and Blinkit both are leading tech companies of India and are powering India's changing lifestyles. While Zomato is focusing on the food delivery and the dining out space in India, Blinkit is basically focused on expanding the quick commerce segment in India. And to basically add on to that, Blinkit is an wholly owned subsidiary of Zomato, and mainly me, both Shubham and I, are were first basically onboarded with Blinkit, and now working both for Blinkit and Zomato. Now, briefly talking about the numbers at Zomato. So Zomato serves over 50 million monthly orders to its 18 million active customers. It does this by with a fleet of over 350,000 delivery partners all across India. And these delivery partners basically help in delivering the hot food to the customers from close to a quarter million restaurant partners. Moving over to Blinkit. So Blinkit basically works on a dark store kind of a model wherein we have small stores, not big warehouses, within the locality, and these help us basically in logistically delivering orders within, let's say, 10 to 15 minutes, or you can say in blink of an eye. And with this model, it has basically it is able to deliver around 12 million monthly orders to around 4 million active users, and it has basically a network of 400 dark stores spread across 19 major cities in India. So yeah, that's what the scale of Zomato and Blinkit looks like, and the current business scenario. Moving on over to Shubham.
Okay, so coming to the main topic of today, that why does Blinkit requires data marts? Before we go into that, we will basically need to understand the scale of data and how the need of data mart arises in the first place. So Blinkit being in the quick commerce segment, fast data analytics becomes essential to drive business basically. And we are having several TBs of transactional data coming from DBs like Postgres, DynamoDB, from various applications, and also our events data that we are fetching from our mobile apps. All this data has to be basically stored and retrieved at a fast pace and in a scalable format. So keeping these points in mind, a data lake is the obvious choice for us to store our data and retrieve it properly. We basically use multiple open table formats like Hive and Iceberg to store this data. And Trino is the primary query engine behind our data lake. Okay. So as you can see in the diagram, we use multiple Trino clusters to support our data lake. We have clusters for, we have an ETL cluster for our Airflow DAGs. We have our ad hoc cluster for our ad hoc analysis, like ad hoc queries that the analysts fire, and our reporting cluster, which is mainly for the dashboards that people use. Okay, so now that the querying part is sorted, users can basically derive insights and metrics from this data via like the BI tools or the scheduled workloads on Airflow. But the blocker here is there is no way for end users to store these derived metrics anywhere, and hence we need to basically recompute. We saw that people were recomputing these metrics every time when it was needed to be fetched, and this is where like data marts come into play. To understand it better, let's consider a simple scenario where one report requires aggregation of past 6 months and the other reports require aggregation of past 1 year in the same data. Without data marts, we will be basically running the same aggregation multiple times, leading to wastage of time and resources. Whereas with data marts, we could simply filter on date and get the same results. So yeah, this was our use case for data marts. And coming and other than this, things that we need to keep in mind while solving data marts at scale is that at Blinkit we have multiple teams and multiple verticals, and each of these verticals have their own data analysts and basically small pods which require building of data marts at scale. And furthermore, due to dynamic nature of our business, the data marts also need to be updated in a very near real-time fashion with a frequency of as low as you can say 15 minutes. And additionally, taking into account our user base, our analysts were already well versed with SQL and Python. So we wanted a solution which can be easily introduced to them because they're already proficient in that. Over to Bhanu to walk through the solutions.
So, to solve this problem of handling various data marts at this with this update frequency, what are the obvious candidates for the solution? So, should we go with Spark, which can basically handle scale and but is complex to use, or should we use a proprietary conventional data warehouse solution, which is easy and intuitive to use, but is costly? So, and the last choice, which is basically the Iceberg connector, we basically decided that it was a clear winner for us. Now, basically going into the pros and cons of each approach, just briefly touching that why we chose the Iceberg connector as the approach. So, while data managed data warehouses may seem like an appealing solution because they are very super easy to use and very intuitive for the end user, they also have very good performance, but this all comes at the cost when your data start scaling. We can There are numerous like cases, and we also basically faced the same challenge wherein we were earlier using a managed data warehouse, and the cost started to rise exponentially uh, with rising scale. Also, there is another major drawback of a managed solution, especially the data warehouse, is that they have a black box design, which makes basically debugging difficult in cases of issues. Next, we also looked at a managed Spark solution. Now, Spark has basically like a very scalable approach, but the ease of use is very limited. And the same goes for the end user. It is very hard to explain for the end user that how how to use Spark. An analyst For an analyst, Spark is a little bit difficult to use, and that's why uh, you know we did not consider this. And in addition, the managed Spark solution is also comes with a license cost. So we thought that we could run our own Spark on a Kubernetes cluster, and this basically uh, reduces the cost, but further increases the complexity. And considering the overall maturity of this Spark on Kubernetes, and the overall community support, which was limited. Uh, which was limited, did not we decided not to go with this approach. Now, coming to the Trino Iceberg connector, it was very easy to implement with its SQL support and the asset guarantee. It basically checked all of our boxes, and it was like a clear winner and an easy choice to make. So over to Shubham, who will explain the implementation details of this Iceberg connector.
Okay. Thank you, Bhanu. Okay, so for the implementation part, like we said, our users were already well versed with SQL and Python, and we doubled down on it and basically identified there were two major flows that the analysts are using. These are the SQL flow and a data frame flow. So let's look it into more depth. The SQL flow is nothing but a simple SQL query that the analysts are already used of writing. They can provide this SQL query, and we can basically convert this SQL query into a simple merge statement, which can be fired upon the Trino cluster only via the Trino Iceberg connector. And the final Iceberg table can be easily abstracted. And user can basically monitor and log everything very easily in their scripts only to debug their applications. While this was solving for 90% of our use cases, there were some complex use cases where we required some enhanced data modeling capabilities of data frames. So for this, basically, we opened up the possibilities of using data frames. So user can pass data frame to the function, and we will basically upload this data frame to a S3 bucket. And on top of that, basically, we can register a Hive table. Once that Hive table is registered, the flow is quite similar to the SQL flow only. From the Hive table, we can basically prepare a select statement, and from that select statement, we can prepare the merge statement, and again, the data can be easily abstracted to the final destination table. So with these two routes, nearly 100% use cases were getting covered, and yeah. Apart from these two approaches, we were like in these two approaches, we were giving the following capabilities to our analysts as well. We are supporting four load types: absurd, append, truncate, and partition override. Basically, when the user specifies a certain load type, we create the corresponding DML statements and power their workloads. For example, for absurd, we power this kind of merge statement as shown in the diagram. For append and truncate and partition override, we basically just write some delete and insert statements and accordingly manipulate the data. Apart from that, for schema evolution, we currently support addition of new columns very easily. And lastly, we also support a concept of incremental key, in which we can basically do some smart absurds by taking an incremental key from user, and on the basis of the incremental key, we decide whether the row should be updated or not. If the value of incremental key being passed in the incremental data is greater than the existing one, we basically absurd the new record. Otherwise, we leave the current record as it is. So, like these were the capabilities that we are providing to our end users, and most of our workloads are currently being powered through this.
So coming to how the Iceberg connector basically helped in our workloads, mostly our write workloads. So currently, like the Iceberg connector is able to power more than 1,000 data marts at Blinkit. Uh, we are able to basically maintain one of our largest transaction tables, which is up close to like 5 TB, and it handles around 10 million absurds daily. Uh, Moving on to a simpler workload, we have like our events table, which has close to 50 TB of data, and we basically are inserting around close to 2 billion records through this Iceberg connector. And overall, if we say like per day, we are writing around 6 terabytes of data, and which approximate to around 44 billion rows in a day. And uh, aggregating these workloads into perspective, 90% of these workloads basically are finished within 5 minutes. And you can say like we also do maintenance with our upsert and insert queries. These account to 2 additional minutes to an overall of a 7 minute ETL workload. So as you can see overall, like we were able to run the Iceberg connector on a scale of an e-commerce company, of an which is basically running in 17 major cities in India, and we were quite happy with the results. And yeah, so moving on, we also want to basically tell that what additional things we required apart from the connector in order to basically derive the whole flow. So uh, iceberg tables basically need to be regularly maintained, and because the regular upserts and inserts create small files, and also each and every upsert or transaction you do on the iceberg table creates a snapshot. So the older snapshots in the directory basically need to be cleaned up when you no longer require them. So a strategy had to be devised to tackle this maintenance problem. So this is the overall architecture that we basically followed to tackle maintenance. So there are basically two paths through which you can achieve maintenance on iceberg tables. One, you can either fire an alter table command through the iceberg connector, or you can use Spark, uh, and basically fire a Spark procedure to basically perform the iceberg maintenance. And currently, we only focus on basically two kinds of two kinds of maintenance. One being the compaction of the small files, which is achieved through rewriting of the data files, and the other being the expiry of the old snapshots. In some scenarios, we also do the rewriting of the manifest files, but with mostly these, the compaction and the expiry, all 90% of the use cases are covered. And so we basically went with a hybrid approach and incorporated both these flows with the help of a very lightweight service. This lightweight service basically feeds from the ETL metadata as well as the Iceberg file metadata, and using both these metadatas, uh, the service is basically able to decide whether a particular table needs to be maintained through Trino or through Spark. And now the obvious question which must be coming to mind would be why we did not use Trino for maintain running all our maintenance. And the answer to that is basically, um, we have basically configured our Trino clusters to be uh, for general purpose. So basically, they are supporting both read and write workloads, and running these heavy maintenance jobs would have basically took a toll on our cluster and increased the cluster size, and hence it was not feasible to run all the maintenance through the Trino connector. Coming on to the future scope, uh, so of the current implementation, so we also plan to basically, uh, in order after the table addition, we also want to add like support the conversion of data types in our schema, the backward compatible data types, also deletion of a column. And apart from that, we also want to make the partitioning a little bit intelligent. Currently, like, we only take the column name on which partitioning has to be done, but we also want to implement an algorithm wherein it is able to decide if that particular column has to be a range based or a hash based bucket partitioned, so that we are able to store our iceberg tables effectively and query them optimally. Over to Shubham.
Yeah. So with this, our writes are mostly sorted, but with the increasing size of our iceberg tables, there's one more area that we need to focus on, that is the reads. Since with the increasing reads, we also see that the performance of read query takes a toll when the size of table increases. To cater to that, we have basically two approaches. First one is indexing. Iceberg already supports Z ordering and puffing index, which helps greatly in optimizing the reads on the table. We are doing POCs for the same and want to incorporate that in coming future. And apart from that, one thing that we can do is table compression. Iceberg supports multiple table compression formats like ZSTD, Snappy, and everything. We are also doing a POC on that and seeing which compression format is helping us the most, considering our data types, the type of our data, and basically which can help us save in S3 costs that we are paying to store the data. So yeah.
Yeah, that's it. So thank you, folks, and for and thank we would like to basically thank Starburst for this opportunity and sharing our work with the Trino community. It was a great experience, and we hope to basically, like, have this future opportunities perhaps in life. Yeah.
Cool. And you can reach out if you want to work on the cool projects like this. You can reach out to us on yes@zomato.com. We are always hiring. And in case of any doubts or any feedback you have for us, you can always reach out to us on our emails. Thank you, folks. Thank
Yeah.
you.
Thank you so much.